All right, guys, welcome back to the second portion of the pre-recorded lesson for Thursday. We're going to take a look at the More on Linear Regression pack because there's a lot more, I think, kind of talking points here than actual examples. And I think talking through a couple of these things is going to be very helpful for the linear regression lab that you guys did with the SAT scores, as well as the work with the Vineyards data set as well. So specifically, I want to really kind of touch on R squared, R, what those are, and talk a little bit about how to calculate some of the values using the calculator as well. But we're going to save kind of the big theoretical kind of construction of R and R squared for class next week. So let's say we have some data, we're pretty certain that it's a scatter plot kind of situation, and we have a really nice thought that a linear model seems like it's going to fit the data. So for example, I got this like nice scatter plot data down here, and it kind of looks like in red that I can kind of get a line of best fit in there. I don't know exactly what the line of best fit looks like, but I get a general sense that maybe there's an association between the x and y variables here. So the question is, how do I find the slope? How do I find the y-intercept of the particular linear model? And we're not actually going to derive those things because we need a little bit of calculus to do that. And specifically, it's going to be multivariable calculus too. So it's a little bit above our heads to actually derive these things. However, there are a couple formulas and a couple ways we can utilize our technology to get at these values, as long as I have the data set. So I do need a data set in order to be able to do some of these calculations. So if you want to calculate some stuff by hand, I can calculate the slope of the linear model using the following formula, taking the correlation coefficient, which we'll talk about in a minute, which is R, and multiplying it by this fraction. Sy represents the standard deviation of the y data, and Sx represents the standard deviation of the x data. Now, both Sx and Sy can be found using our calculator, and I'll show you how to get at those if you would like. But typically, the calculator already knows how to solve for the slope, so we don't necessarily need to use this formula. But I'll show you that those numbers do end up, in fact, being the same. If I would like to calculate the intercept of the linear model, then it's given by the following formula. So the y-intercept is equal to the average of the y data, so y bar, minus b, so what we calculated on the last slide, times the average of the x data. And again, I'm going to show you that indeed we can get those values from our calculator, and everything lines up the way that we expect it to. But like I said about the slope, it's just far easier to go into your calculator and tell your calculator just to calculate the slope number. It already has this formula programmed in, so there's really no need for us to actually do this calculation by hand. But like I said, I'll show you kind of how everything lines up appropriately. These are the instructions to how to get in there, but I'll show that to you as we're working through the example. So here's the example I would like to work through. We're actually going to try to determine the line of best fit using the calculator. Okay, so as I get set up here, just make sure that you have access to your calculator. And what we're going to be doing first is programming in the data into the calculator first. So I'm just going to check OBS. I'm pretty sure you guys can see the calculator when it pops up. Yeah, perfect. Okay, so let's jump back to that example, and you should be able to see my calculator here, and you can follow along as I input this data. Of course, be mindful that you can pause at any time you would like. So right now I'm just in the regular computation mode. So I'm going to hit the mode button and go into the statistics mode, which is number 3. If you're already in statistics mode, you should probably go into mode and statistics mode again, because you're probably not in the 2-variable statistics mode. So far we've been using number 1, which is the single variable statistics mode, to find things like the mean, the median, the IQR, the standard deviation of one variable. But if we go into number 2, you see how it says a plus bx? This is now linear. So now we can input 2 variables and get all of the information we need about the relationship between two variables. So I'm going to hit number 2. That's going to take me into the linear setup for the calculator. Now, you notice it looks a little bit different. We have an X column and a Y column. So I'm going to go ahead and start programming in the X column, just the same way we did before. So the first couple numbers are 0 and 0. You'll notice that the Y numbers we're going to have to kind of scroll back and get to. So right now they're all going to get inputted as 0, but that's okay. Just to kind of skip over them for now. So enter a couple 1s, and then we need 2, 3, 4, 5. 2, 3, 4, 5. Perfect. And then once you have all that data entered, you can just hit the down button on your calculator, and that'll take you back to the top. We're going to use the over to the right button to get into the Y column and start programming in our Y numbers, starting with the number 6. Okay, and hopefully if everything has lined up correctly, 5 and 0 is going to be our last ordered pair that we have to input. And of course, to save this data into the calculator, we just hit the AC button. It feels very counterintuitive, but AC will save that information into the calculator's memory for now. Okay, now what we can do is we can go into that stat dist submenu and see what's there. It's going to look a little bit different. So let's go Shift and number 1 to get into our submenu. So notice that now we have a bunch of different possibilities. We have a new possibility, REG. REG here stands for regression. So if I want anything to do with the line of best fit, I'm going to go into 5. But notice that I can still go into like VAR, for example, and I can still get the standard deviation of the X number or the average of the X number. And now there's new commands in here as well to get Y bar, which is the average of the Y numbers, as well as SY, which is the standard deviation of Y. So you do have access to some new stuff inside of this submenu because we're working now with 2 variables. But let's go ahead and click number 5 and take a look at what's inside here. So we're going to be working with 1, 2, and 3. So A represents our y-intercept, B represents the slope of the linear, the line of best fit, and R is going to represent the correlation coefficient, which we'll talk about in a moment. But let's go ahead and try to get A and B and just kind of get what they are. So for A, I get 5.79. And heading back into that submenu, let's take a look at B. And B comes out to be about negative 1.21, let's say. So according to our calculator, the line of best fit should be y hat is equal to bx plus a. So negative 1.21 times x plus the y-intercept. Okay, so it's bx plus a is how I'm writing it down. You could also write 5.79 minus 1.21x. That's also acceptable, same thing. So this is our line of best fit. This is what the calculator says is a good model based on the data we have. Or I guess the best model based on the data we have. Now what I would like to do is just go back to these couple formulas that we have and show you that indeed this number here is going to come out if I use the formula as well. So I could go in and let's see, what do I need to do? I need to grab some regression stuff. So I need to grab R, which is 3, and I would need to multiply that by a fraction, and the fraction button is going to be a little bit weird. So let's do this, divide by this. Okay, so I'm going to go in and grab some stuff from the variance submenu. So I'm going to grab SY and then divide that by SX. And hopefully this is going to come out to be the exact same B number that we have on screen, and bada boom, there it is. So whether or not you use the formula or whether or not you go directly into the regression submenu to get negative 1.21, it all comes out being the same thing. And I'll let you guys verify that indeed capital A does come out to be the same by taking y bar minus a negative 1.21 times x bar. So you can do that again in the var submenu if that's something that you want to look into. Now what we essentially want to do is we want to, so right now we're not really going to plot that line of best fit. We're going to, I guess we could if we wanted to. We do have a couple points here. We do have some intercepts that would make it fairly easy. Well, no, that's not going to work. Okay, let's say I wanted to plot the line of best fit. We're probably mostly going to be using Microsoft Excel to do this for us, but you know, if I wanted to do it by hand, I think it's a good example. So our model is this. This is the y-intercept. The y-intercept automatically gives us a point on this line, and that point is x equals 0 and y equals 5.79. So I could go ahead and I could plot that y-intercept. That's going to be, maybe I'll just do this in red, so maybe somewhere up in here. So there's our y-intercept. And we could also solve for the x-intercept as well. So what happens if y is equal to 0? If y was equal to 0, we'd get negative 1.21x plus 5.79. We could subtract 5.79 from both sides, and then divide both sides by negative 1.21. So let's go ahead and do that. 5.79 divided by 1.21. And I get an x number of about 4.79. This is called the x-intercept. This is where the line should cross the x-axis. So I could count up 1, 2, 3, 4, and about 4.79. So just drawing kind of, you know, roughly in where that's going to be. And then the idea here is to take our ruler and try to connect these the best we can. Okay, so using red, we're just going to go ahead, connect those 2 points together. And there we go. And that gives us a rough idea of what that line of best fit is going to look like. So yeah, we can totally do this by hand. You just have to use the intercept method. I think that's the easiest way to get at the line of best fit here. Totally doable. But like I said, you have access to Microsoft Excel, so the easiest way is probably to just put this data set into Excel and ask Excel to create the scatter plot and then add in that chart element of the line of best fit. So I think that's probably the easiest way to go about getting the line. Now, what I want to do just for the last couple of minutes of this pre-recorded lesson here is just talk a little bit about r squared and r. So we saw in the lab these two particular numbers. We have r squared, that's called the coefficient of determination, and we have r. It's called the correlation coefficient. The coefficient of determination r squared is really just found by squaring the r value. So r squared is the same thing as little r squared. So we know we can calculate little r squared on our calculator. And if I square that number, I do indeed get capital R squared. I don't know why they use a capital R squared in the notes. I'm not a statistician. If you want to use a little r squared to make it more obvious what you're talking about, that's fine. That's exactly what these researchers do. They're like, hey, screw this. I don't want to use a capital R. And I think that makes sense. So if you want to use a little r, that's fine. I think in the book we're using capital R. If not, I just need to fix my notes. Because the last textbook I was using used a capital R and a small r, and it kind of drove me bonkers. But they're related to each other just by squares or square roots. And the idea with the coefficient of determination is it tells us what proportion of the variation we see in the response variable is actually explained by the linear model that we created. So this wording here is very important. What proportion of the variation of response is explained by the model? That is important. You will hear me say that a lot when working with linear regression kinds of things. And I have a couple examples down here at the bottom that I just want to kind of work through as well. So like I said, the coefficient of determination gives us some kind of idea of how well the model fits the data, fits the variation in the data. Okay? And our r-squared number can be anywhere between 0 and 1. It could be identically equal to 0, and it could be identically equal to 1. If r-squared is equal to 1 exactly, all of the variation is explained by the linear model, and that means every single point of our scatter plot falls onto the line of best fit. These are essentially the lines that you probably would have made in like grade 9 and grade 10 and studied those lines extensively. That very rarely happens in real life when we're doing studies like this. It's more likely that your r-squared is going to fall somewhere in between 0 and 1. Now, on the far side of the spectrum, if your r-squared is getting really close to 0, if it's identically 0, it means that none of the variations explained by the model and all of your points are kind of scattered all over the place. The linear model really doesn't make sense for the data that we have. So you can see the three possible scenarios here of different r-squared values. As the points get kind of tighter and more compact and closer to each other, the r-squared value gets closer and closer to 1. And as the r-squared value drops and gets closer to 0, you can see that the spread or the variation between these points starts to decrease until we get to 0, in which case it's just a random mess of dots all over the place. So that's what r-squared tells us about the model. It gives us some kind of benchmark as to how well fit the model and the data is. Now, it is a little bit of a debatable matter as to what r-squared value is good. I think, from my perspective, I like to see an r-square of about 0.8 or higher, but I know it really depends on the field that you're going into. So, the scientific field probably is going to want a little bit of a higher r-squared value, maybe pushing 6.65 or higher. But some fields might want something smaller. Maybe they're working with small data sets, and 0.3 as their r-squared is a really interesting r-squared value. So it does depend a little bit on your field. So be mindful of that. At the end of the day, what's really helpful is getting more and more pieces of data. So the more and more pieces of data you can get into this scatter plot, the more you can be sure, or the more certain you can become as to whether or not this r-squared is a helpful number. If I only have 3 data points and my r-square value is 1, who cares, right? Who cares? Can I really explain future data, or is it just a fluke that these 3 pieces of data all happen to land on the same line? If I get 100 pieces of data and they are all pretty darn close to that line that I've made, I get like an r-squared value of 0.9, I'm getting excited. There's probably an association between these variables. So more data is always helpful when it comes to working with lines of best fit. So just something to be mindful of there. Now, the correlation coefficient, which is r, tells us kind of similar information. It's going to feel like it tells us similar information compared to r-squared, and that's because they're very much related to each other. So r, the correlation coefficient, tells us essentially 2 things. It tells us how strong the relationship is. It also tells us in what direction the slope is moving for the line of best fit. Okay, so 2 important things: the direction and the strength of the relationship or the association. So I have 6 different plots down here that we want to just have a brief little discussion about. So, and with various values. So I tried to plot some things where, r was equal to 0. You can see that if r is equal to 0, the data isn't really strong. Like I have a really big spread. R is 0, r-squared is 0. It's kind of like independent data. Like these variables don't really have a relationship between each other. But as r starts to get closer and closer to 1 or -1, then that tells me that the strength is a little bit stronger between the 2 variables that we're looking at. So as r gets closer to +1, the strength between, or the association between the variables gets closer in a positive kind of relationship. And as r gets closer to -1, I get a stronger relationship, but in a negative kind of way. So hopefully you can see that illustrated here. Like as I start with 0 and start moving up towards +1, I start to see like a stronger kind of positive relationship. Whereas if I start at 0 and start moving towards -1, I start to see kind of a stronger negative relationship. So that's interesting because R is a number that's going to fluctuate between -1 and +1. It has the potential to be negative, whereas R squared doesn't, because it's a squared number, and a squared number is always between 0 and 1. Okay, so just something to be mindful of as we're interpreting data. Now, one thing we always have to be mindful of with regards to working with lines of best fit is not overstepping our bounds. So what we don't want to do is look at our data and be like, oh, this is a really high R value and a really high R squared value, and be like, you know, variable X is definitely related to variable Y, and in fact, I'm pretty certain that the variable X is causing the response in variable Y. We don't want to step that far. If we try to step that far, we start to get into like hokey pokey territory, like the following graph in the bottom right. So if we look at, for example, the sales in millions of organic foods from 1998 to 2007, and correlate that with autism, we can certainly see, based on the R value, there's a very strong correlation between organic food sales and autism since 1998. So obviously, you know, people buying organic food has been leading to more cases of autism. I think that's completely ridiculous, but it's just a thing for you to be mindful of, right? We can't necessarily step into those bounds because sometimes there's confounding or lurking variables, or we want to be able to replicate the study more and more. The more we can replicate the study, the more likely it is that we can now get causation versus association or correlation. So just be very mindful of that. We don't want to overstep if it's just a singular kind of study. So an example of that would be recently, I think in the last couple of years, we've had enough scientific studies about eating red meat and its connection to certain cancers in the body that now scientists are more confident saying that overconsumption of red meat does cause certain kinds of cancer. So that is a thing that took us very long to figure out, because we wanted to make sure we had enough data to back up that claim and enough replicable data to back up that claim as well. Okay, and I think the last thing we're chatting about with regards to the lab here are residuals and residual plots. So we looked at doing a residual plot in the lab, and essentially a residual plot is a scatter plot of the residual numbers that we get. And we're going to take a look next week on how to calculate those residual numbers. In the lab, I think I can probably flash up some of that data that you guys would have seen in the lab on the Vineyards Excel document. Just to kind of connect back to the lab so you guys can see that. So this was all of the data from the Vineyards lab, and this was kind of our line of best fit with all of our data. And we went through the regression data analysis tool pack bit to get the residual plot. So this is a plot of what we call the residuals, and we'll talk a bit more about those on Tuesday. All of the calculations do pop out down here in Microsoft Excel. So Microsoft Excel does have the capacity to take all of our data points, calculate all the residuals, and plot them as a scatter plot. So this is what we mean by a residual plot. So on our particular notes here, you're going to see in red, what I've done is I've plotted all of the residuals. And a residual plot is helpful in trying to determine whether or not a linear relationship makes sense for our scatter plot. So essentially what we'd like looking at the residual plot is for it to be fairly random and for it not to have a really nice pattern, essentially. So I want to compare it to maybe this residual plot here. And if we look at this residual plot, it kind of looks a little less random than this one, right? So this is pretty random, pretty spread out, doesn't look like it has any, specific trend. But when I look at this one, it almost looks a little parabolic to me, right? Like it kind of looks like it's doing something like this. And so what that tells me when I see a residual plot that looks like that, that tells me that a linear model may not be appropriate for the data that we're looking at. And in green is our data. And you can see maybe that in this particular case, what I've done is I've done an exponential kind of increase in data rather than a linear increase, but I tried to model a line over top of it, and my residuals are telling me, hold up, that might not be the most appropriate thing to do. There's a better kind of model to use for this data. So if your residuals are not random, probably means there's a better kind of model to use for the data. And the last thing we talked about briefly in the lab was the effect of outliers. So the idea that we have, one point that could have really high influence or high leverage on our model. So if we have a data point, so let's say this one over here, that happens to be very far away from a lot of the other data values. So looking at all of the data values in here, I might say that the average of the x's is, maybe somewhere in here. Right, so all of these values kind of in that horizontal movement direction have an x value associated with them, and there's an x bar number associated with all of these things. But I notice that this outlier that's marked with an X is pretty far away. And kind of the same down here. I have this one that's really far away from, like the centermost point would be somewhere over here. And so this distance is pretty far. When you have a data point that's really far away from the average of X bar, we call it high leverage. So it tends to pull the linear model either in an upwards direction or in a downwards direction, depending on whether or not it lies above or below your line of best fit. So I have an example here on this slide where if I include this red point, so this red point here, apologies. This is illustrating a different point called influence. I would not consider this point to have too high of leverage because the average of the x's might be somewhere in here. It doesn't feel like it's that far away from where I would consider the average of the x values. But it does have a big influence, and I definitely use those words in the lab. Influence essentially is any point that has a really big effect on the overall model of the data. So what's happening is if I include this red point, I get the red line of best fit. So in other words, this red point is kind of moving the line of best fit upwards again, but notice it doesn't have high leverage. It's not too far away from what I would consider to be the mean. So these kinds of points are just called influential. So if they're pretty close to X bar, but tend to be like really have like a really big Y or a really low Y value, they're influential without having high leverage. A point could have high leverage and be influential as well, totally. I would consider both, this one that's kind of close to the line of best fit is not super influential. Well, potentially. We'd have to look at the model and kind of make some guesses. But the idea is these outliers potentially can have a really big influence on your line of best fit and on your R-squared value. So if your slope, y-intercept, or R-square value changes a lot after you remove one of these points that looks like it's far away, we would say it's an influential point. And how far it is away from X bar is what determines whether or not it has leverage. So let's take a look at a couple examples here of a couple outliers. So we have an outlier here, an outlier here, and an outlier here. And what we're going to do is we're going to try to kind of figure out whether or not these outliers have high leverage and whether or not they are influential on the model. So whether or not we think they're going to kind of greatly affect our model. And so what I want to do first, I'm going to go through each of these examples and maybe just kind of jot down where I think the mean would be, where I think x bar is going to be. So based on all of the x data here, it's pretty spread out evenly between 0 and 10. So x bar should be somewhere around 5, right? I don't think it's going to be too far away from 5. So let's call x bar somewhere around the middle here. We're also going to have a line of best fit that's probably looking something like this. This is probably roughly our line of best fit. Just by eye. I'm just kind of eyeballing it. Now, the next thing we want to do is try to figure out, is this outlying point, so this point that looks a little bit different from everything else, is it far away from x bar? I don't know. I don't know if it's certainly not the furthest point away from x bar. I mean, there's points down here and up here that are much further away from x bar than this point. So I would probably say that this point doesn't really have a lot of leverage. Certainly not as much as some of the points like way over here, right, or way down here. Those points have much more leverage and will act a little bit more like a teeter-totter compared to the one that we've circled here. Let's talk about influential. Is this point going to try to draw the line of best fit toward it? So in other words, is it going to affect our slope value or affect our r squared value? Probably. This is probably going to be high influence. It's highly likely that if we remove this from our data set and repeat the process of finding the line of best fit, we're going to see that slope or r square value change quite significantly. So I would probably say that this point has a low leverage, but is a pretty influential point overall in this model. I probably am going to want to look at this model again with that point removed to see how it changes. Now, something else we're going to talk about is the residual. The residual, and we'll do a bit more of this on Tuesday, is the distance to the line of best fit. So the residual here is pretty high in case you want to kind of finish off the question, because it is asking here about the residual as well. I would call this like it has a pretty big, a large residual, let's say. It's pretty far away from what I would consider the line of best fit to be. That's how we know it has a pretty big residual number. Okay, let's take a look at the second one over here. So if I look at this data, I got a line of best fit that maybe is going to cut through like this. And I have x values that are, I don't know, between 0 and 10. So again, maybe the average is somewhere here around 5. Okay, and we have our outlier way over here. Does this outlier have high leverage? Heck yes, it is really far away from what I would consider to be the mean. So this is definitely a high leverage kind of outlier. It's really going to drag that line of best fit down in kind of a teeter-totter fashion. That's a high leverage point for sure. It's quite a distance away from what I would consider to be the line of best fit too. So I would say this has a large residual. And finally, we want to take a look at whether or not we think it's influential. So I would probably argue that this is fairly influential due to its high leverage. In other words, this point's really going to be dragging the slope downwards. So I think removing this is probably going to show us that it has a pretty big influence on the model. And the easiest way to check that is to remove that point, go through that process of looking at the new and updated model and compare the new slopes and new r squared values that we get. I would suspect that this is going to have a pretty big influence. Okay, let's take a look at this last one. Again, values are somewhere between 0 and 10, so 5 is probably going to be our average. And we have a line of best fit that's kind of running through something like this. There's our line of best fit. Now, this is an interesting kind of outlier because it's not high leverage, or sorry, it is high leverage, but it's not really going to be super influential on the model, and it also doesn't really have that big of a residual. Like if you notice, it's really going to be really close to the line of best fit, so it's going to have like a small residual, and it's going to probably be non-influential because it lands so close to the line of best fit. But it is pretty far away from the X-bar. So I would probably consider this to have high leverage. So just because a point has high leverage doesn't necessarily mean it has to be influential. I mean, it could be a very odd data point way out there that doesn't really affect the model that much. So yeah, those give you a couple different cases of how to deal with those outliers. And just to finish off, on the slide, they just have a couple assumptions and conditions about using a linear model. So essentially, if you want to use a linear model on your scatter plot, you want to take a look at your points, and you want to kind of argue that the x and the y points that we have kind of come out straight enough. We don't want a very clear, like, parabolic arc, for example, in the relationship between x and y. It doesn't make sense to use a linear model then. If you want to use a linear model, your scatter plot's probably going to look somewhat linear. The best way to check this is to just look at the residual plot on Microsoft Excel. Does it look kind of random, or does the residual plot have some kind of parabolic arc to it? If it does, maybe the linear model doesn't really work for the particular data set that you have. Okay, and obviously if you're going to be working with lines of best fit with your data collection assignment, you do want to check to see if you have any weird outliers. So if you have outliers that affect the line of best fit, do your best to remove them from the data, undergo that process of getting the line of best fit again, and compare. If it greatly affects the data, we might want to consider the data with that outlier removed and try to explain why we don't want to include that outlier. So that's something we can do if we suspect we have an outlier that has like really high influence over the model. So just something to be mindful of as you're kind of working through any examples or working through your own data set. So that's going to finish off the lesson for Thursday, and hopefully kind of get you guys geared up and ready to go for the previous lab as well. So this is going to connect to some of the sections from chapter 3 of the textbook. We'll go over the remaining chapters from section 3 next week on Tuesday. So with that, have a great weekend, guys, and I will see all of you next week.